So today I want to talk about the method of brackets again, but this time I want to deal with the third rule, the third and final rule. Uh, so the first rule I dealt with in a previous video where I computed the Gaussian integral and what was probably maybe two steps. Uh, and that first rule was really secretly Ramanujan's master theorem, written in a slightly different way. And the second rule was just a multidimensional extension of that first rule, and therefore an extension of Ramanujan's master theorem, but only dealt with the case where the number of integrals was equal to the number of sums in the integrand. So rule 3 deals with this case where the number of sums in the integrand is greater than the number of integrals. So maybe this is best exemplified with an example. So today I'm going to talk about the Borwein integrals, which take this form. That should be okay. Okay, so again, these are called Borwein integrals. So these integrals are famous for a really weird reason. If we take, for example, the integral from 0 to infinity of the sinc function, that's the sine over x. Well, this is pi over 2. Okay, not so weird. But what happens when we integrate the sinc function times another sinc function, but where the argument is now x over 3? Well, again, pi over 2. We can keep doing this all the way up to the sine of x over 13. Just keep introducing the next odd number at each step into the product. And again, we get pi over 2. But finally, at the very next step, when we end on 15, so x over 15, suddenly this consistency pattern breaks down. In fact, actually, this integral still is really close to pi over 2. It's approximately pi over 2. I think it's minus something like 2.31 times 10 to the minus 11th. You'll have to check me on that one. This is just from my memory. But it's the point is it's very close. So what causes this breakdown? Well, there's a variety of ways to look at it and to explain it. And today I'm going to use the method of brackets, not to really explain it, but just to kind of show where it does break down in general. Okay, so let's give the general Borwein integral a name. We'll call it I. And let's expand those sinc functions. So we will expand the sine function here, and we'll go ahead and knock out a power of bk and a power of x. So what we have here is the sum from nk equals 0 to infinity of what I'm going to call phi nk. So this is minus 1 to the nk over nk factorial times gamma of nk plus 1 over gamma of 2nk plus 2 times bk to the 2nk. It would be plus 1, but again, we have to divide by this bk here. And same thing for x to the 2nk. Okay, and we'll put our differential here. Okay, so there's actually capital N sums here, okay, because of this product over K and the index here depending on K. All right, so we can transform this into several bracket series. Right? So this is equal to the integral from 0 to infinity of the sum from n1 equals 0 to infinity through the sum from n capital N equals 0 to infinity. And we have a phi n1 through phi nk. We have a gamma of n1 plus 1 through gamma of n, this should be a capital N here, and capital N plus 1. Same thing for the denominator, 2n1 plus 2 through gamma of 2n capital N plus 2. And we have a b1 to the 2n1 through b capital N to the 2n capital N. And of course, we can combine all of the x's. The x is the same for each k. And so what we get is x to the 2n1 plus, we add up everything up to 2n capital N. Now, with the method of brackets, we always just ignore convergence at the start, and we can just move all the sums outside. Everything that doesn't depend on x, we just move outside. And so we get the sum from n1 equals 0 to infinity through n equals 0 to infinity. All of our phi's, these don't depend on x. Our gammas don't depend on x. Same for the denominator. And same for our b's. And what we're left with is the integral of x to this power dx, and we recognize that as the bracket, 2n1 through 2n capital N, and we get this plus 1 from the bracket. This plus 1 comes from that bracket notation, which I introduced in the Gaussian integral video. Okay, so what do we do now? Well, if I wanted to apply the method of brackets here with just this single bracket, I have to make a choice. I have to choose between n1 through n capital N for the index that I solve for. So what the third rule says is to do this for each choice. So there's capital N choices here, and I would apply the method of brackets for each choice of the fixed index. Okay, so let's just pick an arbitrary one. Well, maybe first I should simplify this bracket sum a little bit. And the way we can do that is using the Legendre duplication formula. And what it does is it'll transform this sum to the sum from n1 through n capital N equals 0 to infinity of, and all my phi's are the same. And it's just going to play with these gamma functions here. And what the result will be is 2 to the minus 1 minus 2n1, 2 to the minus 1 minus 2n, and I'll pick up a pi to the capital N over 2. And the denominator will now be gamma of n1 plus 3 halves through gamma of n capital N plus 3 halves. And everything else will stay the same. So I encourage you to look up the Legendre duplication formula and work out this step for yourself. So we can simplify this a little further. This becomes the square root of pi over 2 to the nth power times the sum from 0 to infinity over all of our indices. All of our phi's are the same. And I'm going to put my b's in the numerator now. I've gotten rid of everything else in the numerator. I've pulled it all out. And there's this 4 to the n1 through n capital N, gamma of n1 plus 3 halves through gamma of n capital N plus 3 halves. And I still have this bracket here. Okay, so that was just an effort to simplify the bracket series before I moved on. Sorry about that, I couldn't see. Okay, so what we want to do now is go ahead and apply the method of brackets for each choice of the index. And so since we have symmetry here, what I'm going to do is I'm just going to choose an arbitrary subscript for my index. So I'm going to choose the index nj. I'll put a star here just to indicate that this is the index that I'm fixing. This is the one I'm going to solve for. So what I find is that nj star is equal to minus 1/2 minus the sum from I, sum over I not equal to this j in I. How do I get this? I get this from the vanishing of the bracket, right? I set this thing equal to 0 and I solve for nj star. Okay, so I do this for all j and I get something that looks the same. So I'll only write it down once. And now, what are the n series that are produced by the method of brackets? So I'll keep this here. I'll throw this to the side. Well, I get n of them. Let's index them by ij. And the first one I get from the method of brackets is, well, I apply the method of brackets, which tells me that the solution or the bracket series is given by 1 over the coefficient of nj, which is 2, times this whole summation. Maybe I should include my square root of pi over 2 to the n power first. And I'm going to sum over ni, where I is not equal to j. Right? The method of brackets will get rid of that sum over nj. Okay? And this is 2 times the product over I not equal to j by ni bi to the 2ni over gamma of ni plus 3 halves. So what I've really done here is I have rewritten um, these pieces here, this fraction and these phi's, but the method of brackets is going to do something to the cases where I have an nj. Everything else will stay the same, right? The only thing I'm fixing is the nj. The method of brackets will tell me to plug in for nj in this expression here, and then multiply by gamma of minus nj. Okay, so that's what I'm doing at the moment. Let's see what's left here. So for the nj term, I have to plug in what I have found for nj. So that particular b is bj, and That's to the -1 minus 2 times the sum over I not equal to j of ni. So why is it that? Because what was the exponent of bj? It was 2nj. And I know that nj is this quantity here. So I just multiplied it by 2. And now for the gamma on the bottom, I get gamma of 1 minus the sum over I not equal to j in I. And the last thing that the method of brackets tells me to do is to multiply by gamma of minus nj, which is 1/2 plus the sum over I not equal to j of ni. Okay, so this is what the method of brackets gives us for one of these series. And what the third rule tells us is that we need to sum up the series which converge in a common region unless they're the same. And if one of the bracket series diverges, then we just throw it away. And whatever you get at the end of the day, you could get several solutions which converge in different regions. And those sums that you form are predicted to be the evaluation of the integral. So there are some places where the method of brackets will actually produce an incorrect answer. And I'll talk about those another time. They're not important here, but it is good to keep that in mind. Okay, so let's simplify this. This is a mess. So what do we get? We get the square root of pi over 2 to the n power times 1 over bj times the sum over ni with I not equal to j. We get a gamma of 1/2 plus the sum over I not equal to j of nj over, we get a product I not equal to j of gamma of ni plus 3/2. And we also get a gamma of 1 minus the sum for I not equal to j and I. And lastly, we have a product over I not equal to j of, let's see, this will be minus bi over bj, both squared, to the ni power over ni factorial. Okay, so we can do slightly better here. We can get the square root of pi over 2 to the n power 1 over bj, the sum over ni with I not equal to j. And we can write this using the Polkhammer symbols. So the Polkhammer symbol is given by this notation here. And it's given by gamma of x plus n over gamma of x. So some people will call this the rising factorial. But okay, anyway, the point is using the Polkhammer symbol, which shows up in the definition of the hypergeometric function, we can rewrite this summand in the following form. C. So we can write it as gamma of 1/2 times the polehammer symbol of 1/2 subscript sum from I not equal to j of ni divided by gamma of 3/2 to the n minus 1 power. We get another polehammer symbol of 1 with subscript minus sum from I not equal to j of ni. And we also get a product over I not equal to j of several other polehammer symbols. So if you've never seen the polehammer symbol and you want to familiarize yourself with it, then a good exercise would be getting from here to here. Okay, and what do I have left? I have a product over I not equal to j of this thing up here. That's minus bi squared over bj squared to the ni power over ni factorial. Okay, so the next thing I say comes from a paper on the method of brackets, which says that when you have a polehammer symbol with a negative index, so if you have something of the form minus k m minus m, then we have to use the following rule. So you might call this rule 4 of the method of brackets, but it's just something that researchers noticed while working out examples. So again, the method of brackets is not a rigorous technique for evaluating integrals. It's just a heuristic set of rules. So we have to use it with caution. It can be used to predict the value of an integral, but it can't be used to tell you the value of an integral for sure. Okay, so with this in mind, what we can do now is we can rewrite ij. Okay, so notice we had this negative index polehammer down here. And we can write this now as pi over 2bj, the sum over ni with I not equal to j of 1/2 polehammer sum I not equal to j of ni and a 0 polehammer. I'm writing this in this way for a reason. And a product of 3/2 polehammers with subscript ni. And we still have this product on the end here of our bi squared over bj squared to the ni power over ni factorial. And this thing is exactly the definition of what is called the Loricella, I believe I'm pronouncing that correct, Loricella hypergeometric function of type C. So this is another special function special functions appear a lot when you use the method of brackets. Uh, we get lots of gammas. We get lots of hypergeometric series. In fact, that's what appears the most. So the Loricella hypergeometric series takes several arguments. So it's going to take a moment to write out. In fact, I'm going to need another line here. Okay. So this jth bracket series here is exactly the definition of what's called the Loricella hypergeometric function of type C. And what is known about this thing is that it converges when, so this converges when the sum over I not equal to j, bi over bj is less than 1. Okay, so it's the sum of the square roots of these last terms here. So this converges when this is less than 1. Well, another way to write that is it converges when the sum from over I not equal to j of the absolute value of bi is less than bj. Moreover, let's go back to our series here. We see that because of this zero poke hammer, well, there's going to be a factor of 0 here, except for the case where I is not j. Sorry, for only the case where the ni is equal to 0 for all I not equal to j. Only that term will survive. So the term with ni equal to 0 for all I not equal to j. Only this term will survive. Okay, and when we take just that term in our series here, what we're left with is just pi over 2bj. Everything else is 1. So we find that ij is equal to pi over 2bj when the sum over I not equal to j of bi is less than the magnitude of bj. Okay, so returning back to the example, that famous sequence of examples I was talking about before. So b1 here is just 1. And so the evaluation of that integral should be pi over 2. And indeed it is. It should be pi over 2 all the way up until the sum of b1 through so 7, that's this term here, I believe, is pi over 2, and at the 8th step, suddenly the sum is greater than 1. Right? So 1 plus 3, 1 plus 1/3 plus 1/5 all the way up to 1/15 is going to be greater than 1. And so the method of brackets will predict nothing in this case. And this is exactly where this evaluation of the integral fails. So it's really interesting that the method of brackets will do this for us. But this is just an example that exemplifies that third rule of the method of brackets. So just to summarize really quickly, what does the third rule say? It says transform your integral into bracket series. How do we do that? We pull out the sums outside of the integral, and we collapse the integrals of the variables into brackets, right? Okay, what do we do with that? We apply the method of brackets in every way possible. So in general, you'll have to choose some fixed indices, and there are many choices for these in general. Sometimes there's only one, but in most cases there are many of these, and the method of brackets says to compute all of them. And once you have done that, what it says is, so what you have now is several bracket series, or sorry, not bracket series. You have several basis series. So this gives several basis series. And what do we do? Sum the ones which converge in a common region. So you do this unless the series are the same. When they're the same, then you just discard the extra ones. So we discard repeats. And then we throw away divergent series. And once you've done this, the combined basis series that you've just created should be, in most cases, the actual evaluation of your integral. Okay, so I think we'll leave it there.